Welcome back, class. Tonight we're going to apply the law of conservation of energy to a bit of a more detailed example than we did in our last lecture notes 2 nights ago. But before we do that, I want to remind you of the importance of the law of conservation of energy. It governs all interactions in our universe. So that means energy is always conserved. And thus far, we've only really been talking about mechanical energy. And you learned last night that we can increase or decrease our mechanical energy. Remember, mechanical energy is potential or kinetic energy. We can change our mechanical or potential energy by something called work. So you might be thinking, well, work can increase our energy. We can get energy from doing work on objects. And that's true. We can get kinetic or potential energy from it. But when we get those two forms of energy, overall, we must be losing some other form of energy. So if you are lifting an object, although you're giving that object potential energy, you are actually losing some energy. Your muscles, your body loses some energy when you do that. So total energy is always conserved. Remember, we are just talking about mechanical energy. So let's go back and let's apply the law of conservation of energy to an example that's very common off our coast. We have a lot of brown pelican that live off the coast of Santa Barbara. And actually they mate and breed on Anacapa Island. If you've ever been out there, you see the thousands of brown pelicans out there roosting. So this is an example with a brown pelican cruising at a height of 25 meters over the water at a speed of 15 meters per second. So let's go ahead and look at this. And so here's the bird traveling 15 meters per second, and it's 25 meters over the water. And brown pelican like to dive bomb and catch fish and eat them. So the question is, how fast is the bird traveling when it strikes the water? So let's apply the law of conservation of energy. First, here is the law of conservation of energy. It says that the sums of the potential and kinetic energies are the same at every location, so long as no work is done. So the bird is cruising at 15 meters per second, constant elevation of 25 meters. Does it have potential energy in its initial location, up here above the water? Of course it does. It's above the water. It has a height, so it has a potential energy. Does it have kinetic energy in its initial location? And of course the answer again is yes, because it has a velocity. And we know that kinetic energy is mv squared, 1/2, and potential energy is mgh. So we can substitute those in, and we'll do that in a moment. Another question is, well, what kinds of energy does the bird have when it strikes the water? Down here where it's catching the fish. Does it have potential energy down here? And the answer is no, it does not. It has no height when it strikes the water. Does it have kinetic energy? And the answer is yes. It must have kinetic energy, otherwise it would have lost energy. So it will have kinetic energy when it strikes the water and is about to eat the fish. So let's go ahead and apply this now. So here we see that the bird has potential and kinetic energies in its initial location above the water, flying at 25 meters above the water at 15 meters per second. And here we're showing that it has no potential energy when it strikes the water. Oftentimes our conservation of energy problems, one of these three, if not two of them, will be zero. And we see here that our final potential energy is zero. Now we can write potential energy in terms of mgh and kinetic energy in terms of 1/2 mv squared. So here we have them. And here's another place where some of you made some mistakes today, and that is forgetting that these two velocities are different. This is the velocity when it's in the air, its initial position, and this is the velocity we're going to be solving for when it actually strikes the water. So don't confuse these two v's. This is the final velocity, this is the initial velocity. Because we have mass in every term, like we talked about today in class, we can divide both sides by m. We have to divide every term, this term, and the term on the right by m, and we'll divide the m's out to 1. So now we just have the acceleration due to gravity times the height plus 1/2 of the initial velocity squared equals 1/2 of the final velocity squared. So now we can plug in our values. We know the acceleration due to gravity is 9.8, and the height was 25 meters. And we know the initial velocity was 15 meters per second. And what we're solving for is our final velocity v. We only have one unknown right here. Everything else is been known. So we're going to now calculate. 9.8 times 25 is 245. and we have to square first. Some of you did half times the velocity and then squared that. That's not following order of operations. You want to make sure you follow your order of operations. So 15 squared is 225, and we're going to take half of that and get 112.5. Now we add that to 245, and we get 357.5. That energy equals 1/2 v squared. So how do we get v squared by itself? We're going to multiply both sides by 2, which is the same as dividing both sides by 1/2. Remember, they're reciprocals of each other. So we get 2 times 357.5, which is 715, and that equals our velocity squared. So now all we have to do is square root both sides, and we'll get the final velocity, which is 26.7 meters per second. And we always want to make sure we include a unit. Okay? Velocity is measured in meters per second. And so this is the final velocity. This is the velocity of the bird as it strikes the water. It was going 15 meters per second, and when it strikes the water, it's gained some speed and is actually traveling 26.7 or around 27 meters per second. So there you have an example worked by applying the law of conservation of energy to a situation where we don't have zero kinetic to start with and zero potential to end with. We actually have kinetic energy and potential energy to start with. And so hopefully this will help you solve your problems for your homework. Have a great weekend, and I'll see you in class on Monday.